Let's look at notes for chapter 7.1. This section is dealing with the area between two curves, or we can think of it as two curves, two graphs, two equations, two functions. Okay, so a lot of different ways that we can refer to the graph that we'll be looking at. So the formula, let me first start off with the formula. If we want to find the area between two regions or between two curves, the formula is the definite integral from our left bound to our right bound, and we take the top. We identify which function is the higher function, is the top function, and then we subtract the function that is beneath it. Okay, dx. And if we want to use this formula, we have to make sure that all of our variables, all of our values are in terms of x, that our function are in terms of x, we have dx here, and our bounds are also in terms of x. So we're going to go from the left x value to the right x value. Okay. Now, we've talked about area using definite integrals, but it's always been in this form here, where the curve has always been, or for the most part, has been above the x-axis, and the shaded region that we've been always talking about has always been with the curve and with the x-axis. But technically, this formula is being applied because the top function is the f of x, the bottom function is this y equals 0. So really, we're doing top function minus bottom function, but we never really had to talk about this before because this minus 0 would always just go away, and we would just do the definite integral from our left bound to our right bound of f of x dx, and that will give us the shaded region between the graph and the x-axis. That's what we've been always working from before, right? And when we talked about regions that are below the axis, we knew that whatever the definite integral was, we would have to account for the fact that that this will be negative. But now that we're talking about area, we're always looking for a positive value. So to find the area of this shaded region, again, we can apply the formula top function minus bottom function. In this case, the top function is the y equals 0, and the bottom function is the g of x. So the area in this case is definite integral from c to d. This is from our left to our right bound. Top function y equals 0 minus the bottom function g of x. And so 0 minus g of x will simply give us negative g of x. And so we would always, whenever we found the definite integral of a curve that was below the x-axis, we would always find the definite integral, and then we would just always adapt it by taking the negative. And that's what's happening here as well. Okay. But now we're going to see more situations where we may not be dealing with the x-axis anymore. So in this case, let's say we had two functions, f of x and g of x, and now we're looking for the area between these two shaded regions, and as you can see, the shaded region is not going to include the x-axis at all. So we follow the formula, definite integral from our left bound to our right bound, from a to b, identify the top curve, top function, which in this case is f of x, minus g of x dx. All right. Let's look at example 1. Find the area of the region bounded by y equals x squared and y is equal to 2x plus 3. So y equals x squared is the parabola that we see here. Y equals 2x plus 3 is this linear, the graph that we see here. And we are looking for the shaded region, the enclosed region created from these two graphs, which is the shaded region that I highlighted here. So here are the steps. We're going to first find the point of intersection if it's not given to us already. And the reason for that is that is so that we can locate our left and our right bounds for the region that we're dealing with. Now, the way that we find our points of intersection, we take our two graphs, we set them equal to each other, and then we solve for the variable. Okay, so that's the first thing we do. Second, we have to identify which is the top function and which is the bottom function. And many times you can just look at the graph and identify which one is the top one and which one is the bottom one. Now, something to note is that if it is going to be a top function, it needs to be the top function for the entirety of from the left to the right bound. So if that top function at any point, if it switches to the bottom function or switches to another function, then we have to look at another formula. Okay, so the top function has to be consistent throughout the entire interval, and the bottom function needs to be consistent throughout the entire interval. Okay, so we'll talk a little bit about that later in the case that they're not. And third, we plug into the area formula and we take the integral and we solve using the methods that we've learned. All right, so first step, we're going to find our intersection. So we set the equations equal to each other. We have 2x plus 3. We have x squared. So we set the parabola equation equal to our linear equation. And from here, we can go through factoring steps. So we bring everything over to one side, set equal to 0, factor this to be x minus 3, x plus 1, and this solves to be x equals negative 1 and 3. So these x values tells us our left bound of this shaded region and the right bound of this shaded region. So then we plug into our area formula, which is a definite integral from our left x value to our right x value. Top curve, in this case our top curve, our top function, our top graph is the 2x plus 3. As you can see, that is consistently always the top between the two regions. Now, as we move past these the shaded region, we see that they switch places. But because our interval is only between a and b, we see that in this interval, this 2x plus 3 is consistently always the top function, so that works. And then the x squared is consistently the bottom function, so that works as well. So 2x plus 3, top function, minus the bottom function, the x squared. And then we just go through and we solve. So we know that if we solve this problem, we would just go through our appropriate integral rules. In this case, this is Powell rule for each term. So 2x squared over 2, 3 becomes 3x, x squared becomes x cubed over 3. We can evaluate between our upper and lower bounds, so we always plug in our upper bound first. So 3 goes in for each of the x values. That's f of b. So f of b minus big parentheses, and then now plug in your a value, your lower bound. So negative 1 goes in for all the x values here, and we get negative 1 minus 3 plus 1/3. So this is f of a minus f of b, and we simply distribute, combine terms, and we're left with 11 minus 1/3, which is 32 over 3. So 32 over 3 is the area of the shaded region created by the enclosed region from these two functions.